Magnetic fields run from a magnetic north to a magnetic south pole. Okay, here's a bar magnet. Notice I drew here magnetic field lines coming out of the north and going into the south. And then inside the magnet, they run from south to north. So they are continuous lines, okay, unlike electric field lines that can go to infinity. Okay, so inside they go from south to north and outside north to south. The Earth has a magnetic field, and it turns out that the magnetic field of the Earth can be modeled as a bar magnet, where this is the geographic south and this is the geographic north. So you can see we actually have a magnetic north pole at the geographic south and a magnetic south pole at the geographic north. And I will explain why the field is like that, why there is a magnetic north down here in a short while. Now, if we put a compass needle, which is actually just a tiny magnet, in the magnetic field, okay, the north pole of the compass will be attracted along the field lines to the south pole, and the south pole of this tiny bar magnet compass will be attracted along the field lines to the north pole. So it will line itself up with the magnetic field lines. I have a bar magnet sitting on top of the overhead projector, and I have it projected up here on the whiteboard. And here is a compass, which is just a tiny magnet. And if I move that around, you can see the shape of the field lines around this permanent magnet. Okay, just like I explained earlier on the board. Okay, notice how here the field lines are parallel, and here they point in. Okay, they're parallel. Here they point in, etc. Now this compass here can pivot in 3 dimensions. See that? Ooh. Ooh, yeah. And of course, as I said, the Earth behaves as a bar magnet. And here's a model of the Earth, and I have a bar magnet embedded in it. You can see the shape of the magnetic field lines. Okay, let's take a look at what causes magnetism. A long time ago, a scientist was playing around with a circuit, and there was a magnet nearby, and when he closed the switch, he noticed that the wire near the magnet moved. And this is when it was first proposed that it was moving charge that sets up a magnetic field, which then interacts with another external magnetic field. So the cause of magnetism then is moving charge. If I switch the polarity here, you'll notice that the wire is pulled down. Put it the other way, the wire pops out. So a charge, moving charge, sets up a magnetic field. Now the shape of the field set up by a moving charge was determined by investigating what compass needles do when placed in the vicinity of a current carrying wire. And there's a right-hand rule called right-hand rule number 2, which you can use to remember the shape and direction of the field set up by a moving charge or current. Okay, and I'll show that to you now. Okay, so let's talk about this right-hand rule number 2. Okay, what you do is you point your thumb in the direction of the moving charge, stream of charge, or electric current. And we're assuming that it's a flow of positive charge. So let's say we have positive charge coming out of the board. So we point our thumb in the direction, and then these fingers here, the tips, point in the direction of the field. So we have a counterclockwise directed magnetic field. And the spacing, as I said earlier, is proportional to the strength. So it weakens the further away you are. And it turns out that there's an inverse relationship between the distance and the strength of the field. The symbol for the magnetic field, by the way, is B. So we can write then that B is inversely proportional to the distance away. And of course, it's directly proportional to the amount of current I. So really, the smallest magnet that you can have is the atom. Right? So imagine an electron going around the nucleus of an atom. Here's the nucleus. And let's say the electron is going around like that. So if we use our right-hand rule, point our thumb in the direction of a positive charge, and now of course the electron's negative, so we have to give the opposite of our answer then. So if we point our thumb in the direction of moving positive charge, you can see that the magnetic field, okay, is directed up inside this loop. Okay, let me show you with the hula hoop. Okay, so here is our electron going around the nucleus. Okay, so the electron here is going to your left. My fingers show us the direction of the field, so you notice that they point up inside the loop and down outside the loop. Right, the magnetic field lines go from north to south. Okay, so that's the north pole, and that's the south pole of our tiny magnet. The largest magnet in the world, of course, is the Earth. And we now believe that the magnetic field of the Earth is caused by moving electrons inside the molten core of the Earth. Oh, by the way, actually this would be the reverse direction, right? The south should be up here, and the north should be down here, because remember I used the right-hand rule, which is for positive charge, and since it's an electron, the field is actually directed downward inside the hoop. Okay, because remember the electron, okay, is negatively charged, but the right-hand rule is designed for positive charge. Right, so this is the north, and that's the south. So out here the field goes up, and inside it goes down. So, because there's electrons swirling inside the molten core of the Earth, we can see then that the Earth's magnetic field is probably caused by these moving electrons. Now let's take a look at a model of the Earth and see if we can understand why the north magnetic pole of the Earth is actually in the geographic south region, and the south magnetic pole of the Earth is actually in the geographic north region. Okay, here's North America, and the Earth spins like this, so that pulls electrons along in the inner core. So if we just for a moment imagine that the electrons are positively charged, okay, so we point our thumb in the direction of the moving electrons, my fingertips point in the direction of the field, so you notice that we get a magnetic north up here and a magnetic south down here. But the electron is negative, so it's just the opposite. Okay, so we learned that a moving charge sets up a magnetic field. And if that moving charge travels through an external magnetic field, that is not the one it's set up, it experiences a magnetic force. And we saw that demonstrated earlier when I had a current carrying wire in the vicinity of a magnetic field. You saw that the wire was either pushed up or pulled downward. Okay, so we know that a moving charge sets up a magnetic field of its own. And if that moving charge is in an external magnetic field, that moving charge will experience a magnetic force. And it turns out it will experience a magnetic force as long as it's cutting through the magnetic field. If it runs parallel to the field, it will not experience a magnetic force. Now there's another right-hand rule, it's called right-hand rule number 1, which allows us to predict the direction of the magnetic force on a moving charge in an external magnetic field. And this is the way it works. You point your thumb in the direction of the moving charge. And then these fingers, the charge should be positive, by the way. And then these fingers should point in the direction of the magnetic field that the charge is cutting through. So let's say the field is directed towards you. Notice that my palm of my hand here points down, and that so happens to be the direction of the magnetic force on the moving charge. Okay, let's do another one. Suppose the magnetic field is directed into the board, away from you, and let's say the positive charge is moving to the left. So you point your thumb in the direction of the moving positive charge, your fingers point in the direction of the magnetic field, the palm of the hand points in the direction of the magnetic force, which is down. Now it turns out that that magnetic force is always directed perpendicular to the plane, P-L-A-N-E, formed by the velocity and the magnetic field. So again, the magnetic force is always perpendicular to the plane that is set up by the direction of the velocity and the direction of the magnetic field. So if the charge is traveling to the left and the magnetic field is into the board, okay, this is the plane I'm talking about. The magnetic force is perpendicular to that, and the palm of the hand points downward. Okay, so the magnetic force is downward. What if the positive charge is moving to the right and the magnetic field is directed into the board as before? Well, the magnetic force is directed upward because that's which way the palm of the hand is pointing. And notice that it is perpendicular to the plane formed by the velocity vector and the magnetic field vector. Now there's an equation so that you can get some numbers. The magnetic force is equal to the charge divided by, or multiplied by the speed, multiplied by the magnetic field strength, B, multiplied by the sine of the angle between the direction of the velocity and the direction of the magnetic field, which could be anywhere from 0 degrees to 90 degrees. So when the charge is cutting at right angles to the magnetic field direction, you will get a maximum magnetic force. When the charge is moving parallel to the magnetic field lines, you'll get 0 magnetic force. And remember, again, I'll state that the magnetic force is always directed perpendicular to the plane formed by the velocity vector and the v vector. Now the unit of the magnetic field strength is the Tesla. The unit of charge is the Coulomb. The unit of speed, of course, is the meter per second, and we use degrees for the angle. And the unit of force will be the Newton. Okay, let's use right-hand rule number 1 to predict which way the magnetic force will act on this current carrying wire. So I look at the voltage source. This is the positive terminal. So positive charge is going to come out of this battery, follow the red conductor here. When I close the switch, it will go through there, come around. So it's going to be going to your left through this conductor. So if we use the right-hand rule, okay, we point our thumb in the direction of the moving charge. which is to your left, and then the fingers must point in the direction of the field that this moving charge cuts through. And it turns out that this is the north pole of the horseshoe magnet, and this is the south pole of the horseshoe magnet, and you can figure that out using a compass. Okay, you'll notice here that the white end of this compass is pointing toward this pole here. So that means that this is the north pole, because I do know that the white colored side of this compass needle is south. And how do I know that? Well, because if I put this in the magnetic field of the Earth, okay, I can see that the compass needle, the white end of the compass needle, is pointing toward the magnetic north. Okay, so that means that this is magnetic north. Okay, so when I close the switch, okay, if I point my fingers in the direction of the magnetic field, the palm of the hand points up, so that wire should pop up, which it does. Okay. Okay, what I'm doing here is I'm taking a look at which end of this compass points to the magnetic south of the Earth, which corresponds to the geographic north of the Earth. Okay, and it looks like it's the red tip of this compass. Okay, the red tip that points to the magnetic south. So that means that this red tip is magnetic north, the north pole. So then what I can do here is take this magnet here, which isn't marked, and figure out which end is south. And as you can see here, okay, the red is pointing to that side, the white end is pointing to that side. So this side of this magnet must be the south end. Okay, now knowing that, if I hold it like this, then the magnetic field lines come out of the north and go into the south. So they go down on this side and down on that side. Now, this little spot here is actually the result of electrons striking the screen of this instrument called an oscilloscope. And what I'm going to do is I'm going to bring this magnet into the vicinity of that over here, or I guess over here on this side, and I want to predict using the right-hand rule what will happen to the electron. So we'll first assume that the electron's a positive charge. So I'm going to point my thumb in the direction of the moving positive charge. Remember, it's an electron. And then, since I'm going to hold this magnet over here, and since the field lines go down, right, this is north and this is south, I'm going to point these fingers down, and you notice the palm of the hand points to the right. But since it's an electron, it would be the opposite answer. So that beam there should be pushed to the left when I bring this magnet in. And as you can see, it is. Now if I flip the magnet, then it should be pulled to the right. The right-hand rule.